You have been told eggs are the gold standard for protein, but there is something that quietly demolishes them. One blue-green microbe packing nearly 5 times the protein concentration, and growing up to 30 times more food per acre than beef. Despite this, it is dismissed as pond scum and shut out of the mainstream food system. If the math is so overwhelming, why is it not everywhere? The numbers force us to reconsider what power really hides in our food and what is preventing it from reaching the world. 1 gram of dried spirulina contains more protein than the same amount of eggs, chicken or beef. The numbers are clear. According to USDA data, spirulina delivers 57.5 grams of protein per 100 grams of dry powder. A whole egg, by comparison, contains just 12.6 grams of protein per 100 grams. Skinless chicken breast comes in at 31 grams per 100 grams cooked. The difference isn't subtle, it is staggering. To reach a typical meal's target of 20 grams of protein, the calculation is simple. With spirulina, you need just 35 grams of dry powder. For eggs, you would have to eat about 159 grams, roughly 3 large eggs. Chicken breast requires around 65 grams cooked. Beef, even lean cuts, needs about 77 grams. Spirulina's protein density means you get more with less volume, less weight, and less bulk to digest. These numbers aren't theoretical, they're the same values used by nutrition scientists and dietitians worldwide. The dry weight standard is the benchmark for comparing true protein density, stripping away the water that dilutes most foods. When food is measured this way, spirulina stands alone. Its protein makes up more than half its dry mass. Eggs, often praised as the ultimate protein source, don't even come close, but it's not just about quantity. Spirulina's protein contains all the essential amino acids, just like eggs or chicken. Its digestibility scores, PDCAA values approaching 1.0, put it on par with animal proteins. For iron, spirulina delivers 28.5 milligrams per 100 grams, compared to an egg's 1.8 milligrams. Potassium is another standout, 1,363 milligrams in spirulina, just 138 in eggs. The math doesn't lie, then. Gram for gram, spirulina is the densest protein source in the mainstream food world. It is not a fringe supplement or a novelty powder. It is a protein giant hiding in plain sight. These calculations force a new perspective. Why does a food with such overwhelming numbers remain on the margins, dismissed as little more than pond scum? Spirulina's story is not just about what is inside a spoonful, it is about how quickly that spoonful can be replaced. Under the right conditions, spirulina doubles its biomass every 2 to 3 days. In the world of food production, that kind of speed is almost unheard of. Most crops take months to reach maturity. Chickens need at least 6 weeks to grow. Cattle require years, but a spirulina pond managed with basic care can be harvested again and again in the span of a single week. Productivity is not just about speed, it is about how much food can come from a patch of earth. On a square metre of shallow water, spirulina can yield 10 to 30 grams of dry powder per day. That translates to 30 metric tonnes per hectare each year. By comparison, a hectare of pasture for beef yields less than 1 tonne of edible protein per year. Even the most efficient soy fields top out around 3 tonnes of protein per hectare. Spirulina outpaces them all, not by a little, but by an order of magnitude. This efficiency comes from biology. Spirulina uses sunlight, carbon dioxide, and water to build new protein with minimal waste. There are no roots, no woody stems, no inedible husks. Nearly every cell is edible. Raceway ponds, the standard for commercial spirulina, are shallow and require far less land than fields or feedlots. 1 hectare of spirulina can deliver the annual protein needs of hundreds of people, using a fraction of the water and space demanded by traditional farming. The numbers point to a kind of abundance that feels almost futuristic. If the world needed to scale up protein production without expanding farmland, spirulina's yield per square metre would be hard to beat. In a time of shrinking resources, this is not just a nutritional curiosity, it is a blueprint for how much more the land could give. The potential stretches beyond individual meals, hinting at a food system that could look entirely different from the one we know today. In the heart of 16th century Tenochtitlan, the markets buzzed with trade. Among the maize, chilies and cacao, vendors offered something that caught the attention of outsiders, a green, sun-dried cake called tecuitlatl. Bernardino de Sahagun, the Franciscan chronicler behind the Florentine Codex, described the scene, people skimming blue-green mats from the shallow waters of Lake Texcoco, thickening the harvest, then spreading it on woven reeds to dry under the sun. These cakes, rich in protein and easy to store, were bought by merchants, runners, and those preparing for long journeys. Spanish observers unfamiliar with the food likened its taste to cheese and marvelled at its popularity in the bustling markets. Far from being dismissed as waste, tecuitlatl commanded value and respect, its presence documented in the ledgers and illustrations of the era. A historian notes that tecuitlatl was not an accident of nature, but a curated food intentionally gathered, processed and traded. The deliberate harvesting and sale of spirulina in Aztec society reveal a level of culinary sophistication that challenges any notion of it as mere pond scum. Drying spirulina was never a matter of chance. In the markets of Tenochtitlan, the process began with careful skimming of the lake's surface, gathering the blue-green mats at their peak. These harvests were thickened and then spread onto woven reeds left to dry under the sun until they formed dense, portable cakes. The choice of timing, thickness and drying method reflected an understanding of both preservation and taste, skills passed down through generations. Ethnohistorians point to these details as proof of culinary intent. Tecuitlatl wasn't just a byproduct of the lake, it was shaped, stored and traded with purpose. The dried cakes held up on long journeys, nourishing runners and messengers who needed strength for days at a time. Some accounts describe their use by warriors who relied on the concentrated nutrition for endurance in battle. In a society where food could mean survival, tecuitlatl earned its place alongside maize and beans, not as a last resort, but as a valued staple. The deliberate care in harvesting and drying reveals a food that was respected, not dismissed. Its presence in the market and on the march speaks to a culture that recognized both its power and its potential. Rows of lab notebooks tell a story in numbers and charts. In one, a high-performance liquid chromatography chart traces the amino acid profile of spirulina. Every essential amino acid registers above the detection line: lysine, leucine, methionine, all present in proportions that match or exceed what is found in eggs. Lab technicians note a protein digestibility corrected amino acid score spelled PDCAAS that approaches 1.0. This is the gold standard for protein quality used by nutritionists to compare sources across the food chain. For reference, whole eggs and chicken breast both score 1.0. Spirulina's value hovers just below in the same league, far above most plant proteins. Iron content stands out in the data. At over 25 milligrams per 100 grams, spirulina delivers more than 10 times the iron found in eggs. The lab records show that this iron is mostly in a bioavailable form, meaning it can be absorbed efficiently by the human body. Nutritionists highlight this point since iron deficiency remains one of the most common global health problems. Spirulina's micronutrient profile also includes high levels of potassium, calcium and B vitamins, with riboflavin and niacin rivaling or exceeding amounts in traditional animal proteins. NASA conducted closed-loop life support research in the 1980s and selected spirulina as a candidate for astronaut diets, citing its complete amino acid profile and dense micronutrient content. Their reports detail how a small bioreactor of spirulina could, in theory, provide the daily protein and iron needs for long-term space missions. The documentation from these trials sits alongside more recent nutrition studies, reinforcing the same conclusion. Spirulina is not just a protein supplement, it is a comprehensive food validated by decades of scientific scrutiny. These numbers, drawn from lab benches and peer-reviewed journals, confirm what ancient traders and modern nutritionists both recognized. Spirulina's protein is not just abundant, it is high quality, digestible and paired with essential micronutrients. The evidence from the lab is clear, setting the stage for questions about safety, purity and the barriers that keep this food from wider acceptance. Production of spirulina today is a process shaped by precision and oversight. In certified facilities, every batch begins with a single, identified strain, verified by DNA testing to exclude unwanted species. The water, nutrients, and even the light exposure are tightly controlled. Operators monitor pH, temperature, and mineral content daily, adjusting conditions to keep the culture pure and productive. Once harvested, the fresh spirulina is separated from water and subjected to a drying process that is both fast and gentle. Most facilities use low-temperature drying, typically under 50 degrees Celsius, to preserve nutrients and prevent the formation of unwanted byproducts. Each step from pond to powder is documented in lab notebooks and digital logs. Before any product is released, samples are sent to third-party labs for a panel of tests. Drying is treated as a critical control point. Microcystin assays are standard. These tests look for traces of cyanotoxins, the same toxins that occur in wild pond blooms. The European Union and Australia set the maximum allowable level for microcystins in spirulina at 1 microgram per gram. In practice, certified spirulina regularly tests far below this threshold, with many commercial samples showing less than 0.1 microgram per gram. Heavy metals, including lead, arsenic, cadmium and mercury, are also measured against strict limits. Certificates of analysis, known as COAS, are issued for each lot, listing test results for toxins, metals and microbial counts. These documents are not marketing tools, they are regulatory requirements often posted online for buyers to inspect. Purity protocols extend to the cultivation environment itself. Tanks and raceways are sanitized between cycles, and water is filtered to remove contaminants. Only food-grade inputs are used, and any deviation from the protocol triggers a halt in production. The entire process is governed by Good Manufacturing Practices, called GMP, a standard that requires traceability from the first gram of input to the last gram of powder. The result is a product that can be measured, verified, and trusted. Where wild pond scum carries real risks, controlled spirulina is defined by its predictability. Every batch is accompanied by data, not just claims. In a world where food safety is non-negotiable, this is how a misunderstood organism becomes something that meets the highest bar for purity and reliability. A single regulatory label can decide whether spirulina ends up in a health food aisle or on a dinner plate. In the United States, spirulina is classified as a dietary supplement, not a food. In the European Union, it is often treated as a novel food, a category that triggers a labyrinth of paperwork and laboratory tests. For a small producer, this means facing a price tag that starts at $500,000 for a full safety dossier, sometimes more. The dossier is not just a stack of forms, it demands genetic sequencing to identify the exact strain, 90-day toxicity studies in animals, and compositional analysis to prove each batch is free of contaminants. For most small-scale farmers, the numbers do not add up. An $8,000 bill for a single round of heavy metal and microcystin testing can erase a season's profit. Legal fees and consultant costs often double or triple the burden. Meanwhile, animal agriculture operates in a different financial universe. In the United States alone, livestock industries receive more than $38 billion in subsidies each year. These funds lower feed costs, insure against crop failures, and prop up prices when markets drop. Spirulina, by contrast, gets no such support. Its producers pay out of pocket for every inspection, every test, and every label. The economic playing field tilts sharply. For a protein source that outpaces beef and eggs in yield and efficiency, spirulina faces a wall of regulatory and financial barriers that keep it on the margins. The gatekeeping is not accidental. It is built into the system, shaping which foods reach the mainstream and which remain niche. On the ledger of a small producer, The costs are not just numbers, they are the difference between survival and collapse. On a busy side street in Brooklyn, a chef in a white coat stands over a bowl of risotto tinted a deep electric green. The colour comes not from spinach or peas, but from a few grams of spirulina powder whisked in at the last minute. His menu lists it as Lake Texcoco risotto, a nod to the food's ancient roots and a challenge to the idea that spirulina belongs on a supplement shelf. Diners snap photos, curious about the taste. The chef explains that the protein in their meal, gram for gram, outpaces steak or eggs. He is not alone. Across the country, food innovators are blending spirulina into pestos, breads, and even ice creams, turning what once was dismissed as pond scum into a mark of culinary adventure. At the other end of the spectrum, in a small town in Oregon, a retired schoolteacher runs a microfarm from her backyard. Her photobioreactor, a clear tank with bubbling water and LED strips, costs less than $500 to assemble. Each week she harvests enough spirulina to meet her family's protein needs, drying it on baking sheets and blending it into smoothies or homemade crackers. Neighbours stop by for starter cultures and a small circle of home growers forms around her. The math is simple. A single square metre of tank can yield more protein in a year than a backyard flock of chickens, using a fraction of the space and water. Culinary trend data shows a steady rise in spirulina's use among chefs and home cooks alike. Food blogs chart its journey from health food stores into mainstream kitchens. Starter kits, once rare, now ship worldwide, inviting anyone with sunlight and a bit of curiosity to join in. This grassroots movement reframes spirulina, not as a mystery powder, but as a tool for abundance and self-reliance. As chefs and microfarmers rewrite its story, spirulina's future looks less like a fad and more like a quiet revolution, growing one dish and one backyard at a time. Today, spirulina remains one of the planet's most protein-dense foods, yet regulatory hurdles and old perceptions keep it at the margins. As food insecurity rises and climate shifts threaten agriculture, the quiet abundance of this microbe demands a second look. Sometimes the future of nutrition grows where we least expect it. What would change if we rewrote the story of what counts as food?